Now, as we talk about active transport, there's some terminologies, and I think that these concepts become much easier if we can keep the terminology straight and the relationship. You know, when we move big molecules and big amounts of stuff from one side of the cell to the other, it can take a lot of energy. And so one of the ways we do this, now if we kind of came up with or described a term related to this, we describe this as vesicular transport, a vesicle being a small portion of the membrane that basically buds off and holds a given container, okay, of stuff. And so it serves as a container. So it serves as kind of a mini portion of the cell, and it contains stuff that we're either moving into the cell or moving out. So vesicular transport is simply that. We are using a vesicle to move something. And sometimes that vesicle is moving something into the cell, and we call that endocytosis. And sometimes it's throwing it out of the cell, whether it's supposed to or whether it's a waste product, and we call that exocytosis. So endocytosis, a type of vesicular transport going inside. Exocytosis, a type of vesicular transport going outside. And so we just have to determine, well, why is that substance being taken in, or why is that substance being sent out? We're going to give examples of that, because sometimes, yeah, we need it to go in because it otherwise can't, and sometimes we need it to go out, whether it be a waste product or it's something else we're going to use somewhere else. Okay, either way. So vesicular transport is simply the use of a vesicle. And either we're going in, endocytosis, or we're going out. So an example of this would be receptor-mediated endocytosis. In other words, how does the cell dictate, A, what it wants, and make sure that it's getting what it wants? Okay? From the standpoint of, well, I don't want just everything to be taken in the cell, because some of the stuff I don't want, but certain things I do. So one of the things that the cell does is it produces a given amount of receptor proteins. So these receptors are specific to the thing that it wants to take into the cell. So in this case, we're going to use, for example, we're going to use LDL, low-density lipoprotein receptor-mediated endocytosis. Okay, so next time you get together a group, throw that out and make yourself sound pretty smart. Okay, so we're saying that we have LDL receptor-mediated endocytosis. We're taking low-density lipoproteins, okay, which we commonly refer to again as our bad cholesterol. It's not bad because we use it. Okay, it's just when we have excess that it becomes bad. But we're taking that LDL and we're moving it into the cell, and we're using vesicular transport to do that. So what happens is the LDL, okay, being extracellular, binds to the LDL receptors on the cell. Membrane or proteins within the cell to identify where that vesicle needs to form is protein. It's called Clathrin Protein. It's one of the proteins that helps basically flag that section of the cell membrane to basally pinch off. So it's kind of like taking cookie dough, okay, which should never be cooked, you just eat it. But anyway, you take cookie dough and you got this big ball of cookie dough and you're sneaking a piece before everybody notices, but you're pinching off a piece and then kind of matting down the rest so nobody knows you took it. Okay, but you've pinched it off, but you still have the remaining dough. So what we're doing with the Clathrin protein is we are flagging basically that section that's where the LDL receptors are, and that's where the vesicle should form. And so as the Clathrin moves around the membrane, it forms a Clathrin-coated vesicle. So next, the coat is lost and it leaves the LDL receptors with the LDL inside of that vesicle. Now, we don't talk a great deal about this, but there is a structure within cells called the endosome, and it's kind of the one we're going to talk about the most is what we call lysosome, and it's a vesicle within an organelle within your cells that helps destroy things or break them apart. Not necessarily always completely destroy, but it's going to break things apart for us. Well, the endosome is going to do that on a smaller scale. That basically what we need to do is within that vesicle, it fuses with an endosome to form this larger structure. And the endosome is going to kind of break things apart but not destroy them, that we end up with the LDL receptor proteins then separated from the LDL. And so now those receptor proteins can be recycled but we then have a transport vesicle full of that LDL. So it gives us the product that we're trying to create. So the receptors get recycled, and then we can utilize in our metabolic pathways, we can utilize that LDL. So now our lysosomes are going to break apart that vesicle and allow us to then use that LDL for whatever we want to have take place in the cell. Because there's certain parts that we want to use and certain parts we don't. And so it breaks those apart for us. Okay, so that's an example of receptor-mediated endocytosis. Now, break that term down. Receptor-mediated because the reason the cell knew what it was getting because it built receptors for it. Endocytosis because it was pulled into the cell. Now, another type we probably talk about more is a type of endocytosis referred to as phagocytosis. And so now this is what we refer to as a cellular eating process. Now, very often people would say, well, how is that different from what we just got done talking about? Well, typically, from a mechanism, it's not a whole lot different, but usually this is kind of reserved for the scenario where through endocytosis we're pulling in something foreign, like a bacterium. Okay, we're pulling in something foreign that's going to be destroyed by that cell, specifically by white cells that do this for us. Okay, and we'll talk about the differences in the types of white cells that we have. And so it's kind of the way of eating things, so it is a type of endocytosis, but this is typically kind of reserved for when we're pulling in something foreign. Now, again, if you look at this, it happens in a similar manner, that the cell is going to be able to target the foreign thing. And as we get into the immune system, you're going to find out, well, how does the immune system flag things so that it knows, okay, this is you and this is not you. So this one needs to go away, okay, but this one doesn't. Well, one of the ways we do that are with our antibodies. So the antibodies we produce to disease, they bind to the foreign thing. Now our phagocytes, cells involved in this process, know, okay, I need to eat that one but not that one, because that one's flagged for destruction, but that one's not. Now what if we had a scenario where there were antibodies made against our own cells? So the immune system sees it and says, okay, that's been flagged, so that needs to go away. So I need to destroy, through phagocytosis, I need to destroy that, and it does. Okay, well that's autoimmune disease. So the relationship there is a normal cell was flagged for destruction. We don't want that. We want the abnormal cell flagged for destruction, which phagocytosis is. So we'll get into autoimmune disease later, but that's an example where that confusion comes in. Okay, so that bacterium, let's say in this case, the bacterium was flagged for destruction. Okay, the phagocytic cell comes by through vesicular transport, pulls that bacterium in. It then produces a vesicle containing that bacterium. It then fuses with the destructive organelles of our cell, the lysosome, which then destroys that bacterium and digests it intracellularly. And so it then, in effect, goes away. Now, in situations where we want to pull in large amounts of stuff, it's not specific. When we're trying to basically take from like the blood, okay, and pull certain things into cells, it uses what we call bulk phase endocytosis. And because very often it's a large amount of liquid with stuff in it, okay, we call it penocytosis. So the difference is phagocytosis, we're eating something foreign and solid, versus penocytosis, usually liquid rather than the solid material. So basically it forms a pit and then seals it off as a vesicle. And so again, the difference here is it wasn't something that was flagged, or it wasn't something that bound to a receptor. Okay, it's non-specific in terms of what was pulled in. Now we just want to look at the opposite of what we've been discussing. The opposite being everything we've talked about up to this point with vesicular transport has been pulling it into the cell. Well, now we want to go the other way. So exocytosis, okay, is moving a substance from inside, now moving it outside. And similar to our endocytosis, yeah, it requires a decent amount of energy to do that, a decent amount of ATP. And so the material is formed within a vesicle and then pushes or merges with the cell membrane, so because we don't want to poke a hole in it. And so it pushes the substance out. Now this can basically come in two forms. This is either a secretory product of that cell. In other words, this is something the cell made and now is shipping outside the cell. Okay? Or this is something that, okay, is a waste product. and it says, all right, we're done with this, because our cells don't do well as hoarders. Okay? Many of you have watched on TV the hoarding shows where people just keep amassing this large amount of stuff. They just can't bring themselves to throwing anything away, and so just their living conditions get more difficult because they just get more and more and more stuff and more stuff, and so there's very little room to work. Well, your cells have a similar issue, that if we keep producing things within the cell or taking things within the cell but never getting rid of it as waste product, well, our cells overfill as well. And so our cells don't do well in a hoarding scenario. So they need to get rid of them. And exocytosis is one of the ways we do that. So there are products of that cell that we excrete outside the cell. And so this is just showing the type of exocytosis where this is a normal substance that we need outside and it's being excreted to outside. Now this is another way that we throw cell identity markers onto the cell membrane. So here a substance is moved outside the cell, but it doesn't actually leave. So here within the vesicle we have, for example, glycoproteins that then merge with the cell membrane, and so now they're sitting on the outside of the cell and serving as identity markers or little flags that tell our immune system, okay, this is me, okay, don't get rid of me, okay, and serves that purpose.